Starting with that. Hello, everyone. I'm welcome back to the NASA Cosmic Origins Galaxies SIG talk list. And I'm absolutely thrilled to introduce Daniel Anglés-Alcázar from the University of Connecticut. He is going to talk to us about cosmological hyper-refinement simulations to leverage future great observatories. And this is why I wanted Aaron to at least be here so he can tell me if I get this wrong. But hey, tell us what we're going to expect to see, because Habitable Worlds is supposed to be an observatory. The other two great observatories are all supposed to be observatories, so general astrophysics. And so getting an idea is part of this project. Daniel, would you like to take it away?
Yeah, thank you. Thanks very much. So I'm sharing a screen now. Let me see if this can play. All right. Yeah, thanks very much for the kind invitation. Yeah, very happy to be here to share some of the work that we've been doing on these hyper-refinement simulations to try and make more detailed models so that we can extract more information from future great observatories. So I'd like to start with just showing the animation that you see here in the background. So this is illustrating the gas dynamics that we expect to be feeding supermassive black holes on galaxies at the peak of cosmic activity. So this is a simulation targeting quasar host halo at about redshift 2.5 or so. So a heavily star-forming galaxy. But then here I'd like to point out that we are zooming into the very, very center of the galaxy. So the field of view here is only something like 100 parsecs. So this is very interesting dynamics, very, very close to the black hole. And yet, in order to simulate this as self-consistent as possible, we have to simulate not just the entire galaxy, but even the environment with this galaxy is forming. So a common topic throughout this talk is going to be sort of this challenge of multi-scale physics that we need to understand and be able to accommodate in models. And so, but I'd like to zoom out for a moment. So this is the beautiful cosmic web, the way we believe matter is distributed on large scales in the universe. And this is just an image from a dark matter only simulation. And this is the context where galaxies form. So the centers of halos, gas can cool down and become dense enough that stars form. And of course, collections of stars form galaxies. And in the end, pretty much we use galaxies to trace the structure of the universe. And of course, galaxies are very interesting, beautiful objects. So zooming in onto galaxies, we see the interstellar medium, we see star-forming regions, and then we see very interesting stellar evolution effects. And then we have impact of stellar feedback that can have significant impact on galaxy evolution at different levels. So things like supernovae or radiation from massive stars can disrupt the birth clouds of stars, injecting metals, mass, momentum, energy, displacing the clouds. So in order to understand galaxies, we need to understand these processes. And then zooming in down to the center of the galaxy, by now we know that most massive galaxies, massive enough, host a supermassive black hole at the center. And we also believe that supermassive black holes can play a key role in galaxy evolution. And so the process of accretion, when gas accretes down to the black hole, there is a lot of gravitational potential energy that gets converted into kinetic and thermal energy and radiation. And we have powerful jets and winds ejected that can impact gas on much, much larger scales. And so it's by now, I guess, most people agree that supermassive black holes play a key role in galaxy evolution. And this is, I believe, one of the still one of the most uncertain pieces that we have in our current understanding of galaxy evolution. So, of course, lots of data from the real universe telling us about this connection between supermassive black holes and galaxies. In the local universe, the black hole galaxy correlations, where I'm not sure if people can see the mouse, but yeah, on the top left here, you can see the black hole mass versus galaxy mass. And then lots of studies basically indicating that, well, bigger galaxies host more massive black holes, which is sort of makes sense. But in detail, it's a big challenge to understand how is that the black hole, which is really tiny at the center of the galaxy, how does it know how big the galaxy is or vice versa? And then also very challenging to explain or to investigate when are these connections established. So observations now pushing to higher and higher redshifts are finding that this connection is established at very early times. And now even James Webb is pointing to perhaps even black holes overgrowing galaxies at early times. So lots of interesting questions there. And then other observations suggest that AGN are more common in star-forming galaxies that are massive enough so that they can retain, the gas reservoir. And then AGN are also more common in dense galaxies. So this plot in the middle is showing the stellar mass surface density on 1 kpc scales in the y-axis versus the stellar mass of the host. And the color in the background indicates some sort of average black hole accretion rate for galaxies. So most AGN tend to happen on relatively massive and dense galaxies. But then zooming out to larger volumes in a statistical sense, at the bottom right panel here, we can see that the cosmic star formation history and the black hole growth history in a volume average sense also track each other relatively well. So in this panel, the black line over here corresponds to the cosmic star formation rate density, and then the different colors indicate more like the different estimates of the black hole growth rate per unit volume. So again, both tracking each other fairly well. And of course, there are beautiful observations literally showing giant jets blowing up huge cavities in the halos of galaxies, and plenty of indication for AGN-driven winds having an impact on galaxies. So I'm just listing here some of the many questions related to this topic. So starting from how do supermassive black holes form? What are the masses and birth locations of supermassive black hole seeds? How can they manage to find the centers of galaxies and stay there for long enough so that they can grow efficiently? And then in more detail, what are the triggering mechanisms of AGN at different luminosities or on different regimes? And then, of course, what is the impact of AGN feedback on galaxy evolution? Different channels for AGN feedback and have different effects in different environments. And so I think a telescope like the concept proposed for the Habitable Worlds Observatory as a 6-meter class UV optical infrared telescope in space with high efficiency spectrograph and also imaging capabilities could make for amazing progress in many of these questions. So in particular, just to list some of the things that I'll be excited about would be extending the dynamical black hole mass measurements down to the low mass regime. So this connects directly with theories of the formation of black hole seeds. So these constraints are very important to understand this connection between black holes and galaxies. And then very generically, tomographic studies of the ISM and the circumgalactic medium to be able to derive the physical conditions, composition, and dynamics of gas across scales, which can then be connected to the impact that AGN feedback may have. And so very important also to study broad emission and absorption line outflows from AGN. So these are just some of the aspects that I think having a super Hubble could really help. Now, as more data comes in, higher resolution, more detailed models are needed, I think, to extract as much as possible information from the data. And so, of course, we need models of galaxies in a cosmological context for different regimes. So this is just a quick overview of the types of models that people use depending on the context. So on the right, we have empirical models such as abundance matching or halo occupation models that are very efficient. They allow you to generate mock surveys and then also connect to other simulations as well. They run very, very fast. And then in the other extreme, we have hydro simulations, which are sort of the models that attempt to implement the physics of galaxy formation as explicitly as possible, so following the hydrodynamics and how gas is converted into stars and so on. And so I guess, yeah, we can say more explicit physics on the left, less explicit physics on the right, but then of course, huge difference in the efficiency of models, with the hydro simulations being much slower than other models. So we need all of these different models for different applications. So I don't think we can say that one is better than the other. They just they're good and optimal for different applications. But today I'll focus on hydro simulations. Also, within hydro simulations, there are different kinds of cosmological hydrodynamic simulations. So the first type, we can say large volume simulations. So think of simulating something like 100 megaparsecs cube, something like that, with a resolution of about 1 kiloparsec, where a lot of the important physics is treated at a subgrid level, like how black hole accretion and feedback would be implemented on scales of 1 kiloparsec or so. And a lot of the work, I think, by different groups is on developing more accurate and more physically predictive subgrid models. This is just an image from the SIMBA simulation, but there are, of course, many others. Now, if we want to, so those are great for statistics of populations, many other things, connecting galaxies to large scale structure. But if we really want to study the internal properties of galaxies in detail, we need to zoom in a higher resolution. And so zoom in cosmological hydrodynamic simulations, in that case, most of the computational resources are concentrated on a much smaller region where only a few galaxies are forming. And so now we can afford not just higher resolution, but also more detailed physics. So the hope is that by exploiting this higher resolution, we can implement more physics explicitly and make models depend less and less on free parameters. So that's sort of the goal in that direction. But of course, the limit is that then you only have a few galaxies. So that's the limitation there. And then some other ideas now, for example, contemplate using large volume simulations with uncertain subgrid physics that depend on free parameters, but now running many thousands of them, but in parameters, so that you can look at the statistics of galaxy populations or any other properties that you might be interested in, and then characterize the range of uncertainties due to the subgrid physics, and perhaps use this data to feed machine learning models to make progress in different questions of for galaxy evolution and cosmology. So this is sort of different types of simulations used for different regimes. These are just of course, simulations that I'm involved in. So this is heavily biased to work that I've been doing in the past few years, but there are, of course, many groups doing excellent work in all of these directions. So I'd like to now show very quickly some results from large volume simulations related to black hole properties. So this multi-panel, very heavy figure here comes from a few papers led by Melanie Habotzi, who has done an amazing job at comparing very systematically the properties of black holes in different large volume simulations. So you can see here at the top, Illustris, TNG, Horizon AGN, Eagle, and SIMBA in this case. And here you can see the evolution of the black hole mass function in the top panels, and then the redshift evolution of the average Eddington ratio. So that would be the average black hole accretion rate normalized by the Eddington rate. And at the bottom, the evolution in the number density of AGN for different luminosity beams. So lots of information here, and I cannot sort of stop in the details, but I guess the conclusion that I want to, or the point that I want to make from this is that some of the main trends simulations are agreeing. For example, you can see how the black hole mass function evolves over redshift in some sort of like qualitative way, and most simulations sort of by construction at this level are matching the observed black hole mass function relatively well. They do agree on the overall decline in the Eddington ratios over time down to lower redshifts, and so on. So there are definitely many successes and aspects in which the simulations agree. But then it's also important to recognize that all of these models depend on extensive tuning of parameters to match observations. And so for some of the more detailed questions of black holes and galaxies, we need to ask ourselves whether some results depend just on the specific models that we use and the parameters that we tune, or how much is sort of intrinsic physics that we are learning. So we can now switch to fire simulations, one of these zooming simulations that I mentioned before, where we can reduce some of the uncertainty in subgrid physics by increasing resolution and modeling things like star formation and black hole growth and feedback at higher resolution. So in these simulations, stars form from high density molecular and locally self-gravitating gas, and then stellar feedback, the mass, momentum, energy, metals coming out of supernovae, stellar winds, and radiation are taken directly from Starbus 99. So the idea is basically take as much information as we know from stellar population synthesis models and use that to model those processes in the galaxy formation context, as opposed to sort of having 3 parameters to characterize the impact of galactic winds, for example. And so the idea is now to start from these type of simulations, and I'm going to show in a moment that we can do even better by increasing the resolution of these fire simulations. So these are just some pretty pictures to illustrate that zooming simulations nowadays are really reaching a level of realism, which is quite astonishing. So all of these images here are fire simulations, and they're overimposed on an actual, a true stellar field. So the image in the background here is this is an actual real image of background stars. Yeah, anyway, so quite amazing the level of detail that these simulations are reaching. So what are some interesting aspects of black hole galaxy coevolution that we can begin to study when we have higher resolution? And in particular, in these simulations, standard fire simulations, you can think of modeling black hole physics, accretion and feedback on a scale between 10 and 100 parsecs, something like that. And then interesting things happen when we look at black hole mass versus galaxy mass or bulge mass here in the central panel. So the different lines that you see here represent evolutionary tracks for 4 different galaxies and their corresponding central black hole as they evolve from very early times down to redshift 1. And so what we find in these simulations is that black holes at early times have a very hard time at growing. So you see that these lines are almost horizontal. Black holes cannot grow very much. And then at some point, when the galaxy is about 10 to the 10 solar masses in stars, then accretion becomes much more efficient. And then black holes can sort of convert onto the local scaling relation. And analyzing the simulations, we realize that what happens in these particular simulations is that stellar feedback is very bursty at early times. So the galaxy very often looks like the panel on the top left, with the center of the galaxy devoid of gas, because stellar feedback is just pushing out gas, and so basically not letting the black hole to grow efficiently. But then at later times, the galaxies look more like the panel on the right, where the deeper gravitational potential can retain a nuclear gas reservoir, and this nuclear gas can more efficiently feed black holes. So these are effects that are usually missed in lower resolution simulations, and just emphasize the need for higher and higher resolution models with more detailed physics. Now, this is still, I should say, there is still a lot of uncertainty in this picture here. And also, I should emphasize that many of the groups have seen effects like this with the stellar feedback suppressing black hole growth. Now, it's important to emphasize that the initial black hole mass is still very uncertain. So the location of this horizontal branch could vary up and down a lot, depending on the initial black hole mass. And here we are also assuming some accretion efficiency that could also make these lines change. So it's important to recognize that this is still black hole growth as parameterized on scales of order 100 parsecs. So the question that we wanted to address is, can we do better? Can we get closer and closer to the black hole to estimate this in more detail and as opposed to having to extrapolate from scales of, say, 100 parsecs or a kiloparsec? So the idea of these cosmological hyper-refinement simulations is we choose a snapshot from a given fire simulation that we have, and then we restart the simulation from there, increasing the resolution dynamically as the simulation proceeds. And specifically to investigate black hole growth at the center of the galaxy, what we do is we refine more and more gas that is closer and closer to the black hole. And so this is I'm gonna illustrate how this works. So here you see a scale of about a megaparsec centered around a massive galaxy at the center of the image. And then, so the color scale indicates gas surface density. And then what we're gonna do is zoom in down to the center to basically illustrate the range of scales that now these simulations can handle. And again, for context, this is about redshift 2, a halo mass of about 10 to the 12.5, star formation rate of the central galaxy of a few hundred solar masses per year. So now we go in, you're going to see sort of circles indicating the scales as we proceed. Larger scales, the dynamical times are much longer, so things don't seem to move much. But now that we are zooming in down to the very center of the galaxy, you see that the dynamics are much faster. And then at the end, when we zoom in down to a few parsec scales, you can see that the black hole is here. The location is marked by the cross sign, and it's actually moving. So the black hole is interacting gravitationally with the lopsided stellar disk and gas clamps and all of these complex dynamics. And then now we are zooming back out again to again illustrate the fact that black hole accretion and feedback that originates on really tiny scales, and yet feedback can have a big impact on scales as large as what we see now. And so this is now another illustration of the same type of hyper-refinement simulations, now with different panels corresponding to different scales, from 2 megaparsec scales in the top left all the way down to the central 20 parsecs. And again, this is in a full cosmological context. And these are now showing like mock 3-color images. So this is, perhaps with HWO, this is how galaxies could look like. And so again, looking at the top panels on larger scales, you see that things evolve very slowly. But then when we focus on the very inner region, you see these turbulent gas, and you see these dark filaments, dusty filaments that are blocking the light from stars behind and are feeding the black hole and forming these accretion disks of size of around a parsec, maybe similar to the scale that people usually quote for the torus around black holes, and changing direction very quickly. So lots of very interesting dynamics happening here. Now I have a long list of sort of details that the simulations like this must include in order to model everything cell consistently. So I'd like to emphasize that it's not just about cranking up resolution, but the more resolution you have, the more detailed physics you need to implement for things to make sense. So there is a lot of work in the background to make this happen. All right, so and just so summarizing, the left, this shows the gas surface density distribution at the center of a massive galaxy with a resolution of 30,000 solar masses, which is still more or less state-of-the-art for massive galaxies that are very expensive to simulate. And this is now the same galaxy, but simulated down to a resolution of 30 solar masses per individual gas element. So really, to me, this is like getting new glasses. Suddenly we see all of these details. So now we can ask, okay, what sort of science can we do with it? And one of our goals here was to understand black hole accretion as explicit as possible. So here the panel over here that you see is showing the accretion rate as a function of cosmic time down to redshift 1 more or less for a standard fire simulation. So this estimate of the accretion rate versus time comes from a subgrid model evaluated on scales of about 100 parsecs. So think of this as some sort of reasonable guess for what the accretion could look like if we only know what the gas is doing on a scale of about 100 parsecs. And then what we're going to do is restart simulations switching on this hyper-refinement technique and targeting different phases of the history of this black hole to see if we can model more explicitly what's the actual accretion rate down to much smaller scales. So the lines of different colors here indicate the 3 different phases that we're going to zoom in. And so the first one, and one of our biggest goals for this project, was to see if we could predict inflow rates sufficiently high to explain a bright quasar phase. So this has been a long-standing issue to understand how is that galaxies can funnel down to the black hole enough gas to explain the luminous quasars that we see. And actually, when we choose for this particular galaxy, we chose the snapshot that had the densest, the highest densities at the center. And then now and you can see here sort of the 10 parsec scales, very high gas density. The black hole is moving because it's interacting with a very dense stellar lopsided disk. And then in the top right panel, you can see what is now the actual accretion rate as a function of time measured at subparsec resolution. So there is no subgrid modeling here. We can let the code evolve and just tell us explicitly how much gas is crossing the inner 0.1 parsecs. And to our surprise, in fact, we were able to see that these very extreme conditions are actually conducive for quasar feeding. So we were able to see accretion rates on average of over 6 solar masses per year. Now we may ask, of course, quasars are very rare objects, so these types of conditions shouldn't happen very often. So what we did was to go back only 40 million years early in the history of the same galaxy and then do the same experiment. We hyper-refined the simulation and measured explicitly what's the accretion rate on subparsec scales. And then again, to our surprise, we found that the conditions are very, very different. So only 40 million years earlier, the gas was actually, the center of the galaxy was not as dense, a lot of turbulence on the scales of 100 parsecs, which is what we see here now in the lower left panel, and the accretion rate is dramatically different. So in this case, there is a huge variability in accretion rate on the scales of only a couple of million years. We see accretion rates that can be as high as 10 solar masses per year, so that would be a very luminous quasar, but then very quickly that can go down to like 10 to the minus 3 solar masses per year. So really extreme variability, it was also, again, a big surprise for us. And finally, now we can go and let the galaxy evolve down to redshift 1 or so. And in this case, the galaxy has stabilized, much more massive. The gas fraction is much lower and is forming a very thin disk of gas. And the interesting thing that we found here is that the galaxy develops this central cavity of hot gas, very low density, which we believe is due to gas consumption by star formation and stellar feedback opening up a cavity like this. And what happens is that when the black hole is in the middle of this hot, low-density cavity, it cannot accrete very efficiently. Hot gas doesn't like to fall down to the black hole. And so the black hole is basically not growing at all until the gas from the cavity is destabilized and is torqued by the stars. And then sometimes the black hole can catch one of these filaments or gas clumps that happen to fall like close enough that can be gravitationally captured by the black hole. So here we are waiting for some of those accretion events. And here we go. Now we form a small accretion disk for maybe a couple of million years that feeds the black hole at rates of about between 10% or between 0.1 and 0.01 solar masses per year. So the blue panel at the bottom shows now the type of accretion history that these simulations are predicting. And for us, this was also very interesting because this implies that basically the physics of the ISM, star formation, stellar feedback, and torques are predicting self-consistently some sort of duty cycle for AGN. And again, rather different conditions to what we found in earlier on for this galaxy. So basically 3 tries and then 3 very different conditions, very interesting results across the board. And this is a lot of physics that is, again, missed in standard resolution simulations. So we can also look into many other interesting questions. So for example, we may ask, what is driving the gas flows down to 0.1 parsecs. And then what we found is the gravitational torques from stars dominate angular momentum transport basically on all scales down to like 0.1 parsec or so. And then generally is the stars that live near the gas, the ones that dominate the torque, but sometimes there's very interesting coupling of scales. So if there is a very strong non-axisymmetry in the stars on kiloparsec scales, sometimes the corresponding torque might be as important as the torque provided by a parsec or 10 parsec scale nuclear disk on gas very close to the black hole. So very important to be able to bridge across scales. Then we also studied the connection or lack of connection between star formation and AGN. And so we found that the nuclear star formation rate correlates relatively well with the instantaneous black hole accretion rate, but that doesn't work for the global star formation rate. So the global star formation rate changes on much longer time scales, and so that can explain why observationally it has been difficult to establish such a connection. And then other interesting aspects, for example, take into account how the angular momentum of gas changes significantly on different scales. And so we see in many of these simulations that the parsec scale disks that form can be almost completely randomly oriented relative to the larger scale galaxy disk, which again agrees with observational findings that, for example, jets can be pointing in, or maser disks can be randomly oriented relative to the host. Other interesting things, we demonstrated that it's possible to feed the accretion disk of supermassive black holes as super Eddington regimes, at least for some conditions. And we also found that the accretion rate is very weakly dependent on black hole mass. And this has very strong implications for subgrid models. So that's the other thing that we can do here. We can try to help interpret observations in more detail, but also try to test how good or bad are standard subgrid models that we use in large volume simulations. And so in particular for accretion, it turns out that most simulations nowadays still rely on Bondi accretion to parameterize black hole growth. And we realize that when we compare the prediction of Bondi versus the intrinsic inflow rates that we measure, we realize that Bondi can be very wrong depending on the conditions. So this is not a surprise. Many other people and simulations have shown as similar things, but it's still interesting that most groups still rely on Bondi accretion, and only a few simulations have implemented other models. So I think there is a lot more work that needs to happen in this direction, in particular because depending on how we parameterize black hole accretion, the physics or what we understand, for example, in terms of the physical mechanism driving the black hole galaxy scaling relations can be completely different. So I just want to point out that simulations that use Bondi accretion and then some form of feedback for the AGN, they predict that the black hole galaxy relations are driven by feedback. So the main physical mechanism that occurs in the simulations is feedback self-regulation by the black hole is what dominates the M sigma relation, which is of course a beautiful result. But it turns out that in simulations that we use a model based on gravitational torques to parameterize black hole growth as opposed to Bondi, and then some form of feedback, we can reproduce the same black hole galaxy scaling relations, but in this case, the accretion normalization is what sets the black hole host relation as opposed to feedback. So basically, if we, given an observational constraints of black hole mass versus galaxy mass, we want to understand what is the physics behind this. And at the moment, we have simulations that make they reproduce the same observations, but with completely different physics. We can either basically say that is feedback self-regulation or is accretion. And I think this is still an unsolved problem. So we need to do a lot more detail, and hopefully these hyper-refinement simulations can help us understand the physics more explicitly. Now, a very quick word about, how much can we push this idea of hyper-refinement? So the idea is that, well, at some point, we could hyper-refine enough to actually see the intrinsic accretion disk. And so this is what we've been trying more recently now, after a lot of development. And these are just very recent simulations where now incorporate fire physics on sort of galaxy scales, but then increasing the resolution sort of similar to what we did before, but now we keep increasing the resolution down to a point where we have to switch to a model where stars begin to form individually. And for this, we use the StarForge model of Mike Grudrick and collaborators. And so in the end, these simulations are able to resolve down to scales of about 100 Schwarzschild radii. So the inner boundary here that you see in this panel over here, that inner boundary corresponds to 100 Schwarzschild radii. So this is beginning to resolve the true accretion disk. So there is a lot more physics in these simulations, including non-ideal MHD, multiband M1 radiation, along with the magnetohydrodynamics and individual protostellar feedback. So lots of physics to just allow us to keep pushing down to the accretion disk, and some first results that are very, very interesting. So in agreement with previous work, we found that gravitational torques from stars dominate the angular momentum transport all the way down to subparsec scales. But then the physics changes completely. Very interestingly, at around 0.1 parsec scales, star formation shuts down because the gas becomes optically thick to its own cooling radiation. And there are also very strong magnetic fields that are also providing support against fragmentation. And then we see the formation of very strongly magnetized and turbulent accretion disk, which is very different to what has been seen in many standard accretion disk simulations. So this is very recent stuff, and I think this is like a new avenue for in terms of understanding the physics that dominates on these scales. And I think this is also a frontier in observations to sort of understand more the torus regions or the broadline region of AGN. All right, so let's quickly switch now to feedback. That was all about accretion. Now, modeling feedback is also very challenging. AGN winds or jets are powered from subparsec scales, and they can inject energy all the way to megaparsec scales. And so in hydrodynamic codes, injecting winds accurately is also very challenging. As soon as the winds grow a hot cavity or hot gas, is difficult to model at high resolution in Lagrangian codes. And so what we have done in the fire simulations is, in the same way as we developed this hyper-refinement model to be able to track accretion at higher resolution, here we have implemented a hyper-refinement model to inject AGN winds at higher resolution than what could be possible. That could be so we use new particles that represent the winds at, say, 100 or 1,000 times the resolution. So the animation here is showing the, on the color scale, is showing the propagation of winds. So the winds are injected at 0.1 parsec around the black hole. We assign them some mass outflow rate and velocity with parameters just taken from observations. Velocities typical of BAL winds, broad absorption line winds, and then outflow rates of the same order of the black hole accretion rate. And then we let the winds escape and naturally interact with the surrounding interstellar medium. And we see that, well, some of the winds, well, they are sort of trying to push out the gas from the center, but there is a lot of accretion from the circumgalactic medium, constantly feeding the galaxy. So there is this constant struggle between gas falling in down to the galaxy from the circumgalactic medium and the winds trying to push the gas out, and very, very complex dynamics. So a lot of the winds find parts of this resistance and are able to escape to the circumgalactic medium and then inject energy on those scales. So this now allows us to study these processes also in more detail than is usually possible. And so very quickly, I'm going to just show a couple of examples of things that we can now look at with simulations like this. We can, for example, ask, if we want to understand what is the impact of AGN winds on galaxy evolution, we want to know on what scales are winds in coupling their energy to the surrounding gas. And so this is what this plot on the left is showing. This is showing the radius within which 90% of the injected energy has coupled to the surrounding gas as a function of time. And so on different lines of different colors correspond to AGN winds that we model with different feedback efficiencies. So basically, the red line is the strongest winds, very, very strong quasar winds that very quickly open up a cavity and can travel very far away from the galaxy and begin to couple more and more energy into the circumgalactic medium because they have been able to open up a very big cavity and they can escape. But much weaker winds, like the purple line, they cannot really break out of the galaxy, and so they couple most of their energy into the ISM. So this has very important implications that are also connected to the inferred efficiency of AGN winds. And so this is another, I guess, frontier in this context. We have more and more observations that are quantifying, trying to measure the energetics of AGN-driven winds on different scales. Sorry. And a complication that we have here is that this inferred kinetic efficiency of AGN winds depends on many, many things. It depends on, for once, the intrinsic efficiency of the winds at the injection scale, but it also depends at what distance you are making the measurement. This depends on time and so on. So this is illustrated by the plot over here, showing the kinetic efficiency of AGN winds defined as mechanical energy divided by the volumetric luminosity of the AGN. So that would be the efficiency that we would infer if we measure the mechanical energy on different scales at different distances from the black hole, where again the lines of different colors correspond to winds with different intrinsic efficiencies. So the intrinsic efficiencies are denoted by these horizontal lines of different colors. And so this is just the takeaway from here is basically that the efficiency that we infer on kiloparsec scales or 10 kiloparsec scales might be very, very different from the intrinsic efficiency of winds on much smaller scales. Now, other interesting things that we can do is to study whether AGN winds could have also positive effects and not just negative effects on the star formation in the host galaxy. So previous theoretical models have argued that perhaps AGN winds can compress the ISM gas and make it reach higher densities and therefore perhaps trigger star formation. And some observations suggest that this could happen. But this sort of positive versus negative aspect of AGN feedback has not been explored before in much detail, at least in a cosmological context. So this is what my student, Jonathan Mercedes Feliz, has done. And what he finds is that indeed AGN winds can trigger a star formation locally, but the overall effect is still negative. So this is illustrating here the plot on the left is showing the star formation efficiency as a function of distance from the black hole. And so the blue line here corresponds to a simulation without AGN winds, reaching very, very high star formation efficiencies at the center of the galaxy. And then the orange line corresponds to a simulation with a strong AGN winds, which are shutting down star formation at the center of the galaxy, opening up a cavity of a couple hundred parsecs. But then on certain regions, gas that is compressed by the winds can have higher star formation efficiency. And you can see how this looks in the 2D projection of the star formation efficiency in the panel on the right. So again, the idea is that, well, yes, positive AGN feedback is a very interesting phenomena that may happen only locally, while overall the impact of AGN feedback is negative. And another very fun implication of positive AGN feedback is the plausible formation of very dense star clumps or perhaps even globular clusters that we have identified in the simulations. So this is just illustrating the distribution of stars that we see in this galaxy over a period of 30 million years, while very strong quasar winds were shutting down star formation in the galaxy. So in the absence of winds on the left, we see very dense stellar component, very efficient star formation with very strong feedback. The winds are shutting down star formation, but we see the formation of this very, very dense stellar clump. So this is a clamp with more than 10 to the 7 solar masses concentrated on a scale of around 25 parsecs. And so Jonathan has done very, very detailed analysis of the formation of this dense stellar clamp, concluding that is indeed this rapid pressurization or compression by AGN winds, which is driving the formation of the stellar clamp, converting most of its gas into stars in less than 2 million years. So basically before supernovae can disrupt the cloud, and also reaching high enough densities that radiative feedback is inefficient at regulating star formation. So this could be a smoking gun, perhaps, for positive AGN feedback while the overall galaxy is being like globally quenched. Anyway, I think I'm running out of time. So I'm going to just quickly mention that it's very, very important to convert simulations into observables so that then we can make direct apple-to-apple comparisons to observations. And so and this is a recent paper by Rachel Cochrane, who has done a lot of detailed work deriving observable quantities and implications of radiative transfer effects when we compare simulations and observations. And in particular, this is showing that the obscuration by dust is crucial when we try to make inference about the sizes of galaxies. So I'll just show one very quickly this very interesting effect. In the absence of winds, if we look at a simulated galaxy in the rest frame B band, we see this blue panel on the left, very, very compact galaxy because the stars are really forming very efficiently at the center, right? But this is without taking into account dust obscuration. If we actually do a synthetic observation doing 3D dust continuum radiative transfer, we basically don't see almost any light from the center. And so the galaxy would seem to be much more extended because the dust is obscuring most of the stars at the center. And so we would infer with something like Hubble, we would infer a size, effective size of about 3 kbc. While in the simulation with AGN winds, intrinsically, the galaxy has a larger size. It's less dense at the center. But because the AGN winds are blowing up a lot of the dense dusty gas from the center, there is not so much obscuration. And so we would infer a smaller size. So this is sort of the interesting observable implications that may go in the sort of opposite direction that what we might imagine. Now, we are doing a lot of work recently on trying to model not just broadband photometry and spectral energy distributions, but also modeling emission lines from the far infrared to the ultraviolet. So my student, Nyanjan Roy, is putting together this pipeline where we can take a fire simulation, a snapshot, and then estimate, compute the abundances of different ions using the CHIMES chemistry code by Alex Richins. Then we project all of this into adaptive mesh refinement grids that we feed into the RADEMC 3D code, which does the actual 3D line radiative transfer, and we get mock IFUs out of this. So we get beautiful data cubes for basically many lines from the far infrared to the UV. These are just showing examples of spatially integrated line profiles that we see, and we are using this to study constraints on galactic outflow with different emission lines and trying to interpret galaxy spectra across redshifts. And so I think there is a lot of potential for combining these techniques along with our new hyper-refinement simulations. And I just wanted to illustrate some, we see this galaxy, which is actually a big outflow event, a high redshift driven by stellar feedback. This is in C+, in the far infrared. If we observe this galaxy perfectly face on, the panel on the left, the spatially integrated emission line that you see, the width of the line would really not reflect the outflow. We would completely miss that there is an outflow here. But then, of course, if we see the outflowing ring perfectly etched on, now is that we can see the problem quite clearly. So there is a lot of detailed modeling like this that we can do and exploit the simulations. So in conclusion, cosmological hyper-refinement simulations, I think, open a new avenue to investigate the physics of galaxy formation and black holes in more detail and trying to reduce the uncertainties of subgrid models. And there are tools that are being developed to be able to interpret observations and do apples-to-apples comparison more directly. And so I think the greater and the more detailed observations that we get over time, that the more pressure we theorists have on building more detailed models. So I'll stop here. Thanks very much for your attention. I'm happy to answer any questions.
Fantastic. Thank you very much. So this is when I open the floor to both clapping, but also questions. If you want to raise your hand or just jump in, please start with your questions. I do have questions, but I don't want to dominate question time.
We do have a raised hand. So Yue did raise his or her hand in the middle of the talk, but I didn't interrupt you, Daniel. So let's take a question from Yue.
Okay. Thanks, Daniel. This is an incredibly rich talk. So I have too many questions to ask, but let me just ask a few questions that I'm most interested in. So maybe just one. So am I understanding it correctly that currently you are mostly doing this hyper-refinement on the formation and feedback of galaxies and supermassive black holes at redshift 2 to 3-ish?
That's right. Mm-hmm.
Right. So what's the plan on for predicting scenes at redshift 6? And do you imagine that there might be something dramatically different?
Yeah, great question. So in terms of plans, yeah, a lot of the work that we have done, we have been focusing on like redshift 2, 2.5, trying to model sort of quasars, start forming galaxies at the sort of cosmic peak of activity, but we are super interested in extending to the very high redshift regime to interpret the high C observations by ALMA, UWST, all of the super interesting things happening there. And also at the low redshift, I'm very interested in doing hyper-refinement applied to interpret observations of nearby AGN. I think there is beautiful, highly resolved observations of the nearby universe where we can learn a lot about black hole growth and feedback at very high resolution. So that's definitely the plan. We have a large library of fire simulations that we can use as templates to then do these hyper-refinement simulations. So that's the plan. And then we hope to pass this data through the different pipelines that we have to produce the mock observations. So in terms of what could go different, I guess very, very high redshift conditions, very different. Galaxies super gas rich, I guess super turbulent. So really regime that we have not explored much as this resolution. And I imagine we can get very surprising results in the same way as basically every time that we have done one of these hyper-refinement experiments, it has been like a big surprise on different regimes. So I'm very excited to continue and get to those regimes.
Okay. That's very exciting. Keep me posted. Thanks.
Thanks a lot. Yeah.
I'm looking for hands, otherwise I'm gonna ask one myself. Yeah, Mr. Trung.
Yeah, it's me, Newt. Can you hear me?
Yeah.
Yeah, it's very interesting talk, Daniel. I'm particularly interested in the plot that you showed, the black hole roll over the cosmic time. So the very first thing, so I'm just wondering in that plot, in your simulation, did you already include the feedback, the supermassive black hole feedback in that plot yet or not?
So, yeah, let me see if I can find the plot. Do you mean this one or earlier?
No, the other one, the showing how black hole roll over cosmic time. I think the black hole mass as a function of time, I believe. Yeah.
Okay. Yeah. So I think this one.
Yeah, this thought exactly. Yeah.
Okay. Yeah. So this is not including AGN feedback, meaning that this would be an upper limit to black hole growth because then AGN feedback can shut down its own growth. Now, what we believe is that AGN feedback in this case would not have had an impact on the early phase because the black hole is not really growing very efficiently in that regime. And so, but still, I mean, there is the sort of uncertainties in other aspects, like the efficiency of accretion, that is a free parameter here, or the initial seed mass. And so this is more reflecting the physics of stellar feedback and the multi-phase ISM affecting the early growth. But then, of course, how quickly black holes can converge onto the scaling relations, then that would be impacted by feedback as well. Now, with the a point that I tried to make, but very, very quickly, so was that the physics that dominates the normalization of these scaling relations, that depends on the subgrid models that we used. And so with the particular model that we are using here, based on gravitational torques, we can actually reproduce the same, almost the same scaling relations, either with or without feedback, because the accretion efficiency is what sets this normalization in that model. But that's not true in other models. In most other simulations based on boundary accretion, what sets the normalization is feedback. And so this is, I think, a beautiful example of observations which can be reproduced by totally different models that basically would correspond to different physics dominating. And so that's one example where I believe more detailed models with sort of less free parameters could help us understand this better.
Yeah, that's right. Thank you.
I had a question about this particular plot as well, so I'm glad we're on it. So if you have a really small bulge in a very large galaxy, so it's a really big discrepancy in terms of the scaling relations, that help you discriminate between these kind of growth versus the other kind of growth.
So that could be, for example, a large disk-dominated galaxy with so people have been looking at which components of galaxies correlate better or if they correlate at all with the black hole. And so some people argue that black holes do not correlate with the disk component, only with the bulge. But of course, the black hole galaxy correlations are better established at higher masses, and higher mass galaxies are more like bulge dominated up to the point where we get to sort of elliptical or early type galaxies. And so my understanding is this is still an unsolved issue, I think, connected to others, like whether do these scaling relations evolve with redshift. Some observations indicate that the black holes might be overmassive at higher redshift relative to low redshift, with black holes perhaps being maybe only 100 times smaller than the galaxy, or maybe even just a factor of 10, as some JWST observations are implying now. But then, of course, it's very possible that a lot of these might be affected by biases, because it's easier to see black holes that are overmassive. And so these are still all very big questions that then, the more we learn from the observations, then the better constraints we can put on simulations.
Okay.
Yeah, and
an SC that I'm interested in that has most likely a black hole, but it is 10 to the 12 halo mass and 10 to the 9 bulge mass, so there's a big gap there. I have one more, if everybody will allow me. I have one more question, which is sort of related to the general topic. You do expect, so this is the zooming in on the AGN, so you'd expect the environment of the galaxies itself to affect whether or not they have AGN. Is that right?
The environment of the galaxy?
Yeah. So if it's in a filament, for example, versus in a tendril versus in a void, like the further away it is from the actual filaments of galaxies, exactly.
Yeah.
So it's not sitting in a cluster, but actually on one of those filaments. Your position in there, does that tell you whether or not it has an AGN or not?
So I think a difference would be if we hyper-refine another galaxy. So a galaxy in a filament, that would typically be a lower mass galaxy, possibly with not as high inflow rate down to the center. So that could be a more standard start forming galaxy, approaching the center of this sort of group scale halo. And then I imagine with an AGN, which could be switching on and off different times. So physics like the early suppression by stellar feedback could be affecting the AGN here if it is in that sort of mass and physical regime. But yeah, I mean, other than that, it might be, similar physics, I guess, but just with very different conditions. So I think we don't have examples yet of systems sort of resimulated at high resolution like this. But that's the challenge, right? We need to compile many of these models to understand black hole growth and feedback on different regimes, not just for the big galaxy at the center, but also for sort of all of the satellites or for central galaxies that live in underdense regions, like you were saying. And
Okay.
and I think, there are very interesting questions related to correlation between like quasars or AGN and larger scale structure. Very interesting.
So that's something I had a student work on that. So I think we have some observational evidence for that. But now it's interesting to see what simulations will tell us there. Fantastic. Okay, well, I might follow up on that. We're on the hour exactly. So if there's anybody who has any leftover questions, otherwise we are going to thank Daniel very much for talking to us. This was an information dense but really interesting talk. Thank you so much for giving it. I learned a lot.
Thanks so much for making this happen. It's been fantastic to follow the talks. And thanks everybody for joining.
Yay. For those of you who are still here, there's probably
Thank
more
you.
for people watching the recording. We're looking for speakers for the next academic year. So if you're interested in giving a talk, or would like to nominate someone, especially junior folks, you're welcome to reach out to Benny and me and myself. I have one more announcement, but I just forgot. Let me think. Oh yeah, we do have a extra seminar in 2 weeks by Ann Jeskett. So we'll hear more about from Anne about alignment alpha emitters. So join us in 2 weeks, or look out for our email announcement. All right, thank you everyone. See you.
Thank you.
See you in 2 weeks.
Bye.